Yes, a current limiting fuse or breaker can be used to protect the busing in this scenario. When using a current limiting device, abbreviated as CLD, to protect downstream bus bars, there are several considerations. Firstly, the CLD must be coordinated with the Motor Control Center, or MCC's, overcurrent protection. This is to ensure that it will clear a fault before the MCC protection operates. This coordination is achieved by selecting a CLD with a lower interrupting rating than the MCC protection. Secondly, the CLD must be rated for the maximum available fault current to the line terminals. Thirdly, the CLD should be installed as close as possible to the bus bars to minimize the length of unprotected conductors. Regarding listing requirements, there are no specific listing requirements for series systems when protecting downstream bus bars with current limiting devices. However, these guidelines are recommended. 1. Use devices that are listed by a recognized testing laboratory such as Underwriters Laboratories, or UL, or the Canadian Standards Association, or CSA. 2. Follow the manufacturer's instructions for installation and coordination of the devices. 3. Ensure that the devices are properly maintained and tested regularly. It is recommended to consult with the manufacturer of the MCC and the current limiting device to ensure proper coordination and protection of the busing. This consultation is crucial for verifying the suitability of the selected current limiting device and ensuring that it integrates effectively with the existing MCC components. When selecting a current limiting device, the interrupting rating is a critical parameter. The interrupting rating indicates the maximum fault current that the device can safely interrupt without being damaged or causing an arc flash hazard. It's imperative that the interrupting rating of the CLD is equal to or greater than the maximum available fault current at its installation point. Furthermore, the current rating of the CLD must be appropriately sized to handle the normal operating current of the bus bars it is protecting. Selecting a CLD with a current rating that is too low will result in nuisance tripping, while a current rating that is too high will not provide adequate protection against overloads and short circuits. The location of the CLD is another important factor to consider. The CLD should be installed as close as possible to the bus bars to minimize the length of unprotected conductors. This reduces the potential for faults to occur between the CLD and the bus bars, thereby improving the overall protection scheme. The closer the CLD is to the bus bars, the lower the impedance of the fault current path, which results in a faster and more effective clearing of faults. Coordination between the CLD and the MCC overcurrent protection is essential for ensuring selective coordination. Selective coordination means that only the overcurrent device closest to the fault will trip, minimizing the impact on the rest of the system. This can be achieved through time current curves, which plot the tripping time of the overcurrent devices against the magnitude of the fault current. By comparing the time current curves of the CLD and the MCC overcurrent protection, engineers can ensure that the CLD will trip before the MCC protection for faults downstream of the CLD. The ambient temperature can also affect the performance of current limiting devices. High ambient temperatures can derate the current carrying capacity of the device, which can lead to nuisance tripping. It's important to select a CLD that is rated for the specific ambient temperature conditions in which it will be installed. The manufacturer's specifications will provide derating curves that indicate how the current carrying capacity of the device is affected by temperature. Regular maintenance and testing of current limiting devices are crucial for ensuring their continued reliability. Maintenance activities include inspecting the device for signs of damage, such as cracks or corrosion, and tightening any loose connections. Testing should be performed periodically to verify that the device is operating correctly and that its interrupting rating is still within acceptable limits. Testing can be performed using specialized equipment, such as a primary injection test set, which simulates fault currents and measures the device's response. When installing a current limiting device, it's important to follow the manufacturer's instructions carefully. The instructions will provide detailed information on how to properly install the device, including torque specifications for connections and grounding requirements. Failure to follow the manufacturer's instructions can void the warranty and compromise the performance of the device. It is also important to consider the voltage rating of the current limiting device. The voltage rating must be equal to or greater than the maximum voltage of the circuit in which it is installed. Using a device with an insufficient voltage rating can result in insulation breakdown and arc flash hazards. In addition to current-limiting fuses and breakers, other types of current-limiting devices are available, such as current-limiting reactors and surge-protective devices. Current-limiting reactors are inductive devices that are installed in series with the circuit to limit the magnitude of fault currents. Surge-protective devices are used to protect equipment from transient voltage surges, such as those caused by lightning strikes or switching operations. The NEC, or National Electrical Code, provides specific requirements for the selection and installation of overcurrent protective devices, including current-limiting devices. Section 240.4 addresses the protection of conductors, while Section 240.6 covers the standard ampere ratings for fuses and circuit breakers. Section 240.86 specifically addresses series ratings, which are relevant when using a current-limiting device in conjunction with another overcurrent protective device. It is also important to consider the available short-circuit current at the line terminals of the MCC. This information is typically provided by the utility company or can be calculated using engineering software. The available short-circuit current is used to determine the required interrupting rating of the current-limiting device. When selecting a current-limiting device, it's important to consider the let-through current. The let-through current is the amount of current that the device allows to pass through it during a fault. A lower let-through current indicates a more effective current-limiting device. The let-through current is typically specified by the manufacturer in the device's technical data sheet. In addition to protecting the busbars, current-limiting devices can also be used to protect other components within the MCC, such as motor starters, transformers, and control circuits. By installing current-limiting devices upstream of these components, their exposure to fault currents can be significantly reduced. When using a current-limiting device to protect a motor starter, it's important to coordinate the device with the motor's overload protection. The overload protection is designed to protect the motor from overheating due to excessive current draw. The current-limiting device should be selected to trip before the overload protection operates, thereby preventing damage to the motor. Similarly, when using a current-limiting device to protect a transformer, it's important to coordinate the device with the transformer's overcurrent protection. The transformer's overcurrent protection is designed to protect the transformer from damage due to faults within the transformer itself. The current-limiting device should be selected to trip before the transformer's overcurrent protection operates, thereby preventing damage to the transformer. In the case of control circuits, current-limiting devices can be used to protect sensitive electronic components from damage due to overcurrents. Control circuits often contain components such as programmable logic controllers, or PLCs, relays, and sensors. These components can be easily damaged by overcurrents, so it's important to provide adequate protection. When selecting a current-limiting device for a control circuit, it's important to consider the circuit's voltage, current, and interrupting rating requirements. The device should be selected to trip quickly and reliably in the event of an overcurrent. The impedance of the busbars themselves can also affect the magnitude of the fault current. Busbars with lower impedance will allow higher fault currents to flow, which can increase the risk of damage to the equipment. The impedance of the busbars is determined by their material, size, and length. Copper busbars have lower impedance than aluminum busbars. Larger busbars have lower impedance than smaller busbars. Shorter busbars have lower impedance than longer busbars. The spacing between the busbars can also affect the magnitude of the fault current. Closer spacing between the busbars will result in lower impedance and higher fault currents. Wider spacing between the busbars will result in higher impedance and lower fault currents. The configuration of the busbars can also affect the magnitude of the fault current. A three-phase busbar system will have different fault current characteristics than a single-phase busbar system. The neutral grounding method can also affect the magnitude of the fault current. A solidly grounded system will have higher fault currents than a high resistance grounded system. The type of overcurrent protective device used can also affect the magnitude of the fault current. Current limiting fuses and breakers will reduce the magnitude of the fault current, while non-current limiting devices will not. The location of the fault can also affect the magnitude of the fault current. A fault closer to the source of power will result in a higher fault current than a fault further away from the source of power. The impedance of the source of power can also affect the magnitude of the fault current. A source of power with lower impedance will result in a higher fault current than a source of power with higher impedance. The impedance of the conductors connecting the source of power to the MCC can also affect the magnitude of the fault current. Conductors with lower impedance will allow higher fault currents to flow, while conductors with higher impedance will limit the fault current. The ambient temperature can also affect the magnitude of the fault current. High ambient temperatures will increase the resistance of the conductors and busbars, which will limit the fault current. The presence of harmonics in the electrical system can also affect the magnitude of the fault current. Harmonics are non-sinusoidal currents and voltages that can distort the waveform of the electrical power. Harmonics can increase the peak value of the fault current, which can stress the overcurrent protective devices. The use of power factor correction capacitors can also affect the magnitude of the fault current. Power factor correction capacitors can reduce the impedance of the electrical system, which can increase the fault current. The presence of motors in the electrical system can also affect the magnitude of the fault current. Motors can contribute to the fault current during a fault condition. The size and type of motors in the system will affect the amount of fault current that they contribute. The presence of generators in the electrical system can also affect the magnitude of the fault current. Generators can supply fault current during a fault condition. The size and type of generators in the system will affect the amount of fault current that they supply. The presence of uninterruptible power supplies, or UPSs, in the electrical system can also affect the magnitude of the fault current. UPS can supply fault current during a fault condition. The size and type of UPS in the system will affect the amount of fault current that they supply. The type of load connected to the MCC can also affect the magnitude of the fault current. Different types of loads will have different fault current characteristics. For example, a resistive load will have a different fault current characteristic than an inductive load. The grounding system used in the MCC can also affect the magnitude of the fault current. Different grounding systems will have different fault current characteristics. For example, a solidly grounded system will have a different fault current characteristic than an ungrounded system. The size of the ground conductor used in the MCC can also affect the magnitude of the fault current. A larger ground conductor will provide a lower impedance path for fault current, which can result in a higher fault current. The location of the ground connection in the MCC can also affect the magnitude of the fault current. A ground connection closer to the source of power will result in a higher fault current than a ground connection further away from the source of power. The presence of surge protective devices, or SPDs, in the MCC can also affect the magnitude of the fault current. SPD can divert surge currents away from sensitive equipment, which can reduce the risk of damage during a fault condition. The type of SPD used in the MCC will affect its performance during a fault condition. Different types of SPD will have different surge current ratings and clamping voltages. The location of the SPD in the MCC can also affect their performance during a fault condition. SPD located closer to the source of power will provide better protection against surge currents than SPD located further away from the source of power. The coordination of the overcurrent protective devices in the MCC is essential for ensuring that only the device closest to the fault will trip. This coordination can be achieved through the use of time current curves, which plot the tripping time of the overcurrent devices against the magnitude of the fault current. By comparing the time current curves of the overcurrent devices, engineers can ensure that they will trip selectively. The maintenance and testing of the overcurrent protective devices in the MCC is essential for ensuring their continued reliability. Maintenance activities include inspecting the devices for signs of damage such as cracks or corrosion, and tightening any loose connections. Testing should be performed periodically to verify that the devices are operating correctly and that their interrupting rating is still within acceptable limits. The documentation of the electrical system is essential for ensuring that it is properly maintained and operated. The documentation should include drawings, specifications, and operating instructions for all of the equipment in the system. The documentation should also include a record of all maintenance and testing activities.